All right. Hi, everyone. I'm Perry. I'm an engineer with Atlassian on the analytics platform team. Our team builds and runs Atlassian's data analytics platforms. And today we're going to tell you all about how we're rebuilding our internal analytical lakehouse, which we call Socrates. I've also got Chen here with me, and in the second half of this session, he's going to take you on a deep dive of one of the biggest innovations in our design, which is the Declarative Lakehouse. And I'll give you a little teaser to make sure that you stick around for that, which is that we're using Kubernetes to manage our lakehouse. Just in case you don't know Atlassian, we're the company behind Jira and Confluence and Bitbucket and Trello and Loom and about 15 more of your favorite team collaboration products. So let's start by sizing up our current lakehouse. We're pretty big by most people's standards, with over 7,000 monthly users and over 70 petabytes of data stored. On the surface, these numbers look great. Our aggressive self-service and low-friction onboarding strategy has paid off. We're a big success, right? But then when you take a closer look, it's kind of hard to argue that these are healthy statistics, because we've got 26 tables per user and 10 terabytes per user. So imagine you're an analyst in our lakehouse. How do you think you're going to go about finding your way to the right data set when there are 188,000 data sets? There's no production designation to speak of. Everything kind of just exists in the same environment. Everything is a first-class citizen, regardless of whether it's a data engineering single source of truth or a data scientist's abandoned experiment from 3 years ago. So we're in a strange spot. We're wildly successful. We're widely adopted. We're Atlassian's data operating system. But there are some big problems under the surface, so something needed to be done. And if something needs to be done, what is that something? What should our next generation data lakehouse look like? What are the big shifts that we need to make? So for us, the big shifts were obviously moving into Unity Catalog, which to us actually means two things. It means moving out of the Hive metastore, because we're currently using AWS Glue, and it means changing our data access policy system from Amazon IAM to Unity Catalog. We also want to introduce environments and formalizing what environments even mean in data lakehouses. We want to be more opinionated about how the lakehouse works. We are a lakehouse and not a lake, and so we don't want people scripting against S3 buckets anymore. We want production data pipelines. We want a fit-for-purpose data governance system for every definition of data governance, and there are a few definitions going around. We want a declarative deployment system with metadata treated as a first-class citizen, rather than being a crowdsourced afterthought. And we want a consistent information architecture that covers the whole lakehouse, broadly along the lines of data mesh. And so when we looked at all of these things, we realized pretty quickly that this was going to have to be a big bang build. If we tried to just evolve in place, picking off one or two of these big shifts at a time, we'd have easily spent half a decade working through that list, by which point there would have already been a next generation. And so we kicked it all off as a big project, which we call Socrates vNext, which is to build our next generation lakehouse. And it always helps to explain why things are named the way they are, so I should explain that we call our internal lakehouse Socrates, which is a reference to the Socratic method. So with all that intro out of the way, here's the agenda, which covers most of the big points from our list of what the next generation lakehouse looks like. So I'm going to take you through the data access policy changes, environments, and the physical layout that make up those environments. And then I'm going to take you on a quick overview, because we don't have that much time, of how we're thinking about opinionated capabilities and opinionated development lifecycle before handing over to Chen, who will take you on a deep dive of our declarative deployment system. So let's start at the start, the move from IAM to Unity Catalog. And so for this section, I'm not going to talk so much about what next generation looks like, because I think that's pretty easy. It's 100% adoption of Unity Catalog. The hard part here is charting a course from IAM to Unity Catalog safely and without leaking data. And so for this section, I'm going to talk about how we're moving to the next generation, because it's much trickier than it seems at first. So to cut right to the chase, running IAM alongside Unity Catalog creates potentially dangerous situations due to the fundamentally different models. With Amazon IAM, users get their S3 permissions from the IAM instance profile, which is attached to the EC2 instances that make up the cluster. So in effect, the Databricks cluster access control lists are the point at which our policies are enforced. Whereas with Unity Catalog, users get their permissions directly from Unity Catalog grants. And so IAM and Unity are operating on different principles. By principles, I mean identities, right? IAM operates on the cluster, while Unity operates on the user. And so this means that the two schemes can overlap, And as a platform team, we found that to be quite risky. So let's take a simple example of something that we could build with S3 bucket policies and IAM. We've got 3 buckets. Job 1 can read from bucket 1 and write to bucket 2, and job 2 can read the results and write it to bucket 3. And you could imagine as like an ingestion pipeline with sensitive data being landed at the source, and then a few pipelines to mask and then aggregate the data on its way down to the consumption layer where the users will read it. We've also got a cluster that's used by data engineers, which can read from all 3 buckets for debugging, and a warehouse, which can read from the output bucket. So now let's assume that we're moving to Unity Catalog in place, like the dangerous thing. So we'll bring in some new granular permissions, allowing one of the data engineers to look at the specific tables in this pipeline. Not the whole bucket, just the specific tables. And because Unity Catalog operates on the user run in the compute, it actually doesn't matter where this data engineer runs their command. No matter where they are, they can read the sensitive table. And so then let's assume that the user connects to the warehouse because it's fast, which is great. That's what we love about Unity Catalog. Permissions belong to the users, and they can use those permissions wherever they want to work. But this warehouse actually has write access into another bucket via IAM. So let's say it's a results bucket where the data scientists can write the results of their work to share with each other. And it's completely open access, everyone can see everything, and it's actually totally safe under the IAM model because it's not possible to leak sensitive data into that bucket. Only the warehouse can write into the bucket, and the warehouse only has access to safe data. But you can see where I'm going with this though, right? The data engineer now has a dangerous set of permissions. They can read from the sensitive data set, courtesy of who they are, but they can also, oh no, what's happened there? I'm good. They can also, I'll start that bit again. The data engineer has a dangerous set of permissions. They can read the sensitive data set, courtesy of who they are, but they can also write to the results bucket, courtesy of where they are. Cool. And it is worth saying at this point as well that this is kind of like a trivial problem at a small scale. So if we only had like 100 users and 10 buckets, this is kind of an easy problem to solve. But you can see that with 188,000 tables across 800 buckets and 7,000 users and 7 years of like historical IAM policies, as a platform team, that's kind of too big for us to accept as a risk. So I got to there. And so to cut to the chase again, here's how we're approaching the solution. We're declaring the current Lakehouse, the whole thing, to be a legacy environment. And then we're making new accounts with new environments inside them with new rules alongside. And then conceptually, we're going to put a virtual wall in place with IAM operating on the classic environment and Unity Catalog in the new environments. And so I won't have time to dig into the mechanics of how this is actually implemented, like the back and forward bit, but at a conceptual level, it's limited governed access back and forth. And it's largely based on Delta sharing, if that sort of helps you imagine how it works. So we'll start then with 4 environments that everyone understands. And we'll sort of build the design up from there. A key design concept that we're adhering to is that every environment must have a clear purpose. So let's talk about the purposes. These 4 environments exist with the purpose of putting a data product into production. And so what is production? This is kind of the easiest one to explain because everyone knows what production is. But aside from the standard meaning, in our architecture, all consumption happens from this environment. Pipelines consuming from each other happen in this environment, and humans consume from this environment, but they physically work somewhere else, which we'll get to later. And then everything in production needs to meet a minimum set of governance requirements. Staging is also reasonably universally understood, but we spell out a few things explicitly for our system, which is that it's a pre-production environment for testing. It's designed to be as close to production as possible, including the governance systems, and it exists to identify issues in data pipeline code before they reach production. It's not where you identify issues with data, it's where you identify issues with code. Now this one's a little bit unique. Honestly, it doesn't even get used that often, but it's here for 2 main reasons. One of which is for load testing and performance tuning if you're building a pipeline, and the other is for user-facing previews, including formal UAT. Oh. There. And then finally, we have development, which is where data products are built. Contrary to many people's expectations, this is not where the data scientists work, but we'll get to that bit soon. This is explicitly for data product development. So if you're not aiming to take a data product to production, which is the purpose of these environments, then this is not the environment for you. It is very good though, like we're investing a huge amount of effort, we're making this a productive environment for data engineers. It's just not for everyone, and it's especially not for consumption. So before we talk about consumers then, Let's talk about the different kinds of developers who work in the Lakehouse. Because the 4 environments that we've covered so far are all for use by data product developers. But what about the platform developers? What about our team? Where do we work and where do we test? So for this, we've added the concept of platform environments, 4 of them specifically. So Socrates is platform production. Everything here is considered production by the platform developers. And what we mean by that is if there's an outage in Socrates development, then that's a trigger for an incident response. We'll wake up our on-call engineer at 3 a.m. if Socrates development goes down. Data engineers are our customers, and when Socrates development goes down, they can't work. So some of the SLAs might be a little bit different between these environments, but to us, everything in Socrates is production. So then platform staging, which we called Mocrates, is a full replica of Socrates. This is where we perform integration testing and that sort of thing to ensure that all of our platform capabilities work together before we ship them to production. And a test failure here will block deployments to Socrates, which helps keep Socrates healthy for producers and consumers. Platform local development, which we've called Locrates, is where our platform developers work on new features. This has a reduced set of environments, but it has a lot of local access to AWS and Databricks APIs to help with development and debugging. And then finally, we have our proof of concept environment, which we call Pocrates, which is primarily for testing out all of the fantastic new features that Databricks gives us via public and private previews, but we're trying to hold firm on a policy of no previews in Socrates production. So Pocrates goes a long way to helping us trial those new features without breaking our rule. And if you think all of these names are dumb, we're only just getting started because Chen has named all of his stuff after Pokemon. So there's still a few more environments to cover though. All of these environments exist to build pipelines. And so we're going to call these things pipeline environments, which of course implies the existence of user environments. And our first user environment, currently the only one, but conceptually there can be more, is called Workbench. And the purpose of Workbench is for human consumers to consume data products from production. In this environment, users can read governed data from production, and they can read and write ungoverned data within the Workbench environment. So most of our users will only ever use the Workbench. You can think things like insights and exploratory analysis and ad hoc queries, published analysis, all that sort of stuff happens here. And so now with the Workbench environment added, this is essentially the complete map of environments in our new architecture. So that was all a bit conceptual. Let's now look at the physical layer. Firstly, each of the platform environments gets its own Databricks account, not workspace, account. This gives us complete isolation. Nothing that happens in Mocrates can impact Socrates. This also implies a single metastore per lake, because metastores cannot cross accounts, and this is again a good thing. It's intentional to have complete isolation between the platform environments. Looking now at the Databricks workspaces within each of these accounts, this is how we've set it up. There's a control plane, which is used by platform management services to administer the lake. For account-level APIs, we talk directly to the account, but there are still a whole bunch of workspace-level APIs that we need to talk to, and the control plane workspace is what we use to do that. We've also got this workspace set up for any metastore management operations, like any data things that we need to do happen via this workspace, and some occasional platform maintenance scripts. And whilst we haven't hit any triggers for this yet, we're conceptually ready to shard any of the environments if we need to work around limits or quotas. So it's probably not hugely surprising then that the AWS accounts are laid out in exactly the same way as the workspaces. When it comes to catalogs in the metastore, there's a little bit more going on here. For pipeline environments, we have a catalog per environment. That's pretty simple. And then for the Workbench, we have a number of different catalogs to meet different needs. Personal provides personal schemas for anyone who wants one. You can save anything you like in your personal schema, but sharing is blocked by policy. So this is how we prevent data leakage, is by saying that you could only write into your personal schema and you can't share outside your personal schema, totally preventing data leakage. Project provides project schemas, which would be shared by small teams working on time-boxed projects where there is some sharing allowed. Published provides a place where you can publish final data sets that support key pieces of analysis so that they can be preserved for future generations of analysis. For example, if you make a business decision off a data set, you should save that data set as a published data set. The one thing we won't budge on here, though, is that no human can ever write to production. Everything that happens in the production catalog must happen in the production workspace. And humans are only ever allowed to write data in the Workbench. And because of the catalogs, they're only allowed to write into those catalogs. So we spent a lot of time thinking about the rules between these environments. Yeah, this is one worth taking a photo of. I spent weeks on this. At the end of the day, what we ended up landing on came out to be quite simple. And the rough rule of thumb here is that environments can read from themselves and write to themselves, but they can also read from the higher environments. Production can only read and write to production. Staging can read and write to staging, but can also read from production where the specific data set policy allows it. And so these are, of course, like the maximum possible permissions. We're not just granting open access for everything. If you want to make use of these cross-environment permissions, then you have to grant them explicitly. So you can think of these as like a high watermark for permissions rather than being open access. And a core idea behind these rules is that we have to acknowledge that data is different to software. In most cases, it's just not going to be possible to have strict environment isolation in a data lakehouse. There are all sorts of bugs and scaling issues and data quality issues that only emerge when you're working with production data. And so, of course, there are some cases where we must isolate, like when working with customer data. We have to be strict and enforce strict separation and blind deployments to production when we're working with customer data. But for everything else, when the data isn't particularly sensitive, we think it's the right thing to do to allow production data to be read from the lower environments, but the data product owner always remains in control. It's a capability that's there when needed rather than just mandating everything being open. And so being much more opinionated then is a theme that cuts across a lot of what we're doing with this new architecture. But there are two key areas of opinionation that I'm going to touch on today. One is that we've got one clear way to complete each task. And two is that we have a coherent global information architecture. So here's a Venn diagram with a square. I think I'm allowed to do Venn diagrams with squares, rectangle, which has different capabilities that AWS and Databricks support. And I'll have to double check a few of these, but I'm pretty sure we have all of these running in our current environment. And it's kind of impressive that we can do so many things with just two vendors. But should we be doing so many things? This is a huge surface area. It's impossible to support, it's impossible to govern, it's impossible to provide any sort of SLAs at the platform level, and it's impossible to get a complete view of lineage. So we've realized that we just can't keep working this way. We can't keep saying yes to every feature that comes along. What we need then is an opinionated view on what capabilities the Lakehouse needs to provide. And we need to select the best of breed for each of those capabilities. Now this diagram is about a year out of date, so don't bother taking photos. But I'm not going to drill into it. But the key point is how we're thinking about the capabilities. We're being very opinionated about what we are and what we aren't and how users will work on our platform. And so just to call out a few of the things, they're not on the diagram, this has all happened since then, but a few of the key opinionated capabilities that we're providing are that we're going to provide a streaming ingestion service that uses Kinesis with Spark structured streaming. We've got a wrapper around that. We're going to provide transformation of data within the lake using dbt running on a SQL warehouse. We've got a wrapper around that. Interactive consumption is always going to default to using SQL warehouses running via DB-SQL or notebooks. We will have all-purpose clusters available, but in very limited configurations to support R and Python analysis, not pipelines, and ad hoc ML training. And so another part of the design here is that by being opinionated about how these capabilities are used and putting the appropriate abstractions in front of them, we can continue to update our capabilities over time. So if our opinion about the best of breed tooling, for example, data quality changes, then in most cases we can just change out the provider with minimal impact to our users. And so that lowers the cost of lake evolution in future, and it also helps us prevent vendor lock-in. Now, I don't have time to go into all of the details of our information architecture. It could kind of be a whole talk by itself. But the key point is that we have an opinionated information architecture with a globally defined set of domains and a really strict model for how the data layers are to be arranged within a data product. We've got rules about how transformations in one data product can interface with each of the other layers in a different data product. We've got standard column names and join key conventions and all that sort of stuff. It's also worth saying that we're building kind of towards a data mesh architecture, but it's our interpretation of data mesh. It's opinionated, but they're our opinions, and we think that they'll work for our business. And finally, one last thing before I hand over to Chen is to talk at a really high level about how Atlassians are going to use all of this, and specifically the data product developers and the data engineers who'll be seeing the biggest change to the way that they work. Most of the time, data engineers will be working locally in their IDE of choice. As good as Databricks is, nothing beats your favorite IDE, especially when you're working with code and config. And so we built a CLI that wraps around many of the key local DBT commands, and it can deploy straight to development via Socrates Gateway. which is our authentication proxy that sits in front of Databricks. So through this proxy, everyone who's working on a data product can essentially assume a service principal associated with their data product, ensuring that every member of the development team has their pipelines run as the same identity and has access to the same permissions when they're building their pipelines. And we've even got some clever tooling which can go and interrogate the environment after the pipeline has run, which helps the data engineers to fill out all of the YAML config files that Chen is going to talk about in the next half of the talk. So when the engineer is happy with their work, they can push their code to Bitbucket, and Bitbucket Pipelines then goes and deploys the changes to the required environment. We can support branch deploys to the development environment and full deployments to all of the other environments with varying levels of governance depending on the environment. So for example, staging and production both require PRGB, which is peer review and green build. And Chen will talk a bit more about what actually happens in there, but at the workflow level, this is how it works. There's a certain amount of flexibility here as well. So we can support different patterns of teamwork. Different teams might have different preferences or might have different needs at different phases of a data product's lifecycle. As far as we're concerned, all of these environments exist to help teams get to production. That's the only purpose. And so if a team doesn't want to use all of these lower environments, they don't have to. This is an example of how a team could work primarily in development with a little bit of debugging and test and then just deploy straight to production. If their tests pass and they meet the governance requirements, go nuts, skip staging. It's a feature, not a requirement. But for the team who does want to use staging, their flow might look a little bit more like this. When their commits get merged to the main branch, the data product automatically gets deployed to staging, and then an engineer can perform any manual checks that they want to do in staging before clicking a button to deploy to production. And for really big data products with overlapping feature branches that require a little bit more coordinated testing, teams could even use a double PR process if they wanted to, with approvals required to merge into the staging branch and then again to get into the main branch. So with all that, I'm done. I'm going to hand over to Chen, who's going to take you on a deep dive of our declarative deployment system.
Cool, thanks, Barry. So now that all the architects have finished drawing the pictures, somebody has to go and build it. And that's what we're going to talk about in this section, is how we built it, why we built it that way, and hopefully we can do a quick 5-minute demo at the end. It won't be live, I'm not brave enough. Firstly, we need to figure out what we want, and our goal is to build an opinionated data platform. What that really means to us is that we want the data platform to be governed. We need to be able to enforce everything that Perry has said before makes sense and holds in the data lake. It needs to be observable. We need to know what's in the lake. This is good for us because it means we can take new directions and new decisions. It's also good for our users because it means they get things like discovery and lineage and trust and all those buzzwords people like. It also needs to be scalable. We have 7,000 users, as was mentioned before. We're outnumbered more than 700 to 1, so if we do something bad, we're going to get lynched. This is roughly what Socrates looked like in the past. This is our old, classic environment. And how this would work is that users would go into the lake and build things. Some things they won't be able to build themselves, like S3 buckets or interactive clusters. They'll reach out to the platform team via a ticket. And things other than that, like their logic and pipelines and notebooks, they just pop into Databricks and start writing code. In addition to this, we have a metadata service, data catalog. You can think of things like Data Hub are also in the space. They go into the lake and try and scrape out the current state of the lake and kind of tell us what's happening. So if you kind of go over our requirements from before, we can see that it's not very well governed. We do have security policies, but what I mean here is users can go into the lake and do what they want. So a user could make a table called Pikachu and fill it with our mal data and say, we report from a table called Pikachu. This is not very useful to anyone. We can't stop users from creating thousands of different pipelines and thousands of different pipeline deployment strategies, because again, they just go into the lake and do what they want. It's not very scalable. You can see that the platform team is in the way. We currently maintain 100,000 lines of Terraform for our users. We maintain hundreds of support tickets every month, and we want to stop doing that. And lastly, it's sort of observable. We do have the service that runs around and tries its best to make sense of the spaghetti that's in the lake, but we suffer from data integrity issues. You can have tables which relate to each other that don't really make sense, and you can have a lack of richness in the metadata you have. So sometimes we can say this table exists, but we have no idea why it exists or who owns it and stuff like that. So as Perry alluded to before, in vNext, we're changing this. With Socrates, we're trying to flip our entire relationship with metadata. So in this case, metadata is the first-class citizen of the lake, and before anything happens in the lake, the user needs to tell us what they're planning to do. This has a few benefits, the biggest one of which is that users are telling us what they want to happen and not how that happens. So as Perry was alluding to before with the capabilities, a user might tell us, I want to ingest data, but they don't care whether that's ingested via Fivetran or via a custom tool or via something else. I don't know. They just tell us, I want data ingested. They register that, and we figure out how to get that data where they want it to go. This also means we have a system of record for metadata that we can validate before anything appears in the lake. It means that the whole lake makes sense, and we can enforce that it makes sense before anything happens. Based on all this declaration that the user's registered, we can provision resources for them. And this is a pretty big carrot. Users shouldn't need to be experts with like every platform technology that we choose to adopt. And this is our way out of that. It also means that it's very scalable. The platform team is completely not in the loop. We provision things on behalf of users. And because it's automated, it's also consistent and reproducible. Cool. To do this, we've introduced kind of 3 capabilities. The first of which is called Fluid. Fluid is a language for data. It's a language that users write to tell us what they want to happen. We have a system called Vaporeon, which is my favorite. And its job is to store that data and make it a reality in the lake. And obviously, we have Socrates, which is what Perry has been talking about. So we can look at Fluid first. Fluid is a language for data. It's probably best illustrated by an example. So at its core, Fluid is a set of YAML descriptors. You can think of things like CloudFormation or like hacky Terraform, I guess. And so users will tell us like what they want to happen. There's already 2 cool things we can see here. So first is that there's a summary field, and we can enforce that the summary field is set. This kind of helps to answer the question of why things exist in the lake. Obviously, we aren't like passing this through like an AI model to like figure out, I don't know, is the summary good? Although probably could have had a better talk if we said that. Anyway, and the other thing is we're covering extra metadata. So here we have this consume layer declaration on this database. This isn't used for provisioning. It's used by us to make sure that users can follow the platform policies. Next, we have a table. Tables are fairly verbose, and I'm sorry that the thing at the bottom is covering a bit of it. But again, users are telling us what they want. Another thing we have here is lineage declarations down the bottom. And so we could, for example, have a rule that says, you have an attribute here called bar, that's static data, and it draws at lineage from this other column called Baz. If Baz is a UGC column, we might say, why are you transforming UGC into static data? And we can catch this before anything actually happens, like the data never moves. And finally, we also have policies. This is just another example of a descriptor. A few more cool things here. If you've ever tried adding a policy in Unity, you have seen that you can add a policy, but you never know why that policy exists. And so again, having more metadata richness here means we can have things like that. It means we can have historical audit over what policies have and what their intention was. Fluid, at its core, are these components. I've talked about the ones on the left. We also have declarations for things like data products, which are like cohesive units of data, and flows, which are our words for data pipelines. There's actually like a lot of Fluid things. There's these on the screen and more that I haven't listed here. We aren't going to talk about them today. They have perhaps more specialized use cases. Cool. So now that users have figured out how they can declare something that they want to exist in the platform, we need to actually do something with that. And that's where Vaporeon comes into play. So Vaporeon's job is to take one of those descriptors we had before, store it, validate it, and output something as a result. So specifically, this means that Vaporeon is our system of record for metadata. It knows about what's in the lake. It lets us validate that what users have declared makes sense. It enforces our opinions on what the platform should look like. It orchestrates the provisioning of that data. It lets users to interact with it in a self-serve way, and it can extend over multiple platforms. And for example, if you have a data streaming platform that's adjacent to Socrates, the user doesn't really care what platform they're running on. They just care that the data moves from A to B in a sensible fashion. In order to do this, Vaporeon is based around Kubernetes. And this is pretty cool. We don't actually use Kubernetes here for its container orchestration capabilities, although we do that as well. The main thing we're taking away from Kubernetes is its object model. So for anyone who hasn't worked with Kubernetes before, I have this like YAML file on the left. That's called our intended state or a manifest. And in this case, I'm saying I want a deployment that runs 3 replicas of this container. Internally, what Kubernetes does is it lets you store that descriptor into a database within a certain namespace. It runs a workload called an operator, which watches for changes in this namespace and tries to reconcile the actual state of the world with your intended state over here. So for example, if I change my replicas to 2 and store that into the namespace, Kubernetes is going to see my intended state is to have 2 replicas. I have 3. It's going to delete the one in the middle to try and reconcile the actual and intended states of the world. Everything I've talked about here, the implementation is specific to deployments, and so if you didn't get that, it doesn't matter. But the core concept here of storing an object into a store, like database, watching for changes on it, and reacting is fairly generic. And you can extend this however you want. So you can have a whatever operator, whatever manifest that gets stored into Kubernetes. You can have a whatever operator that watches that and does things. And so if we try and draw some lines to what we had before, we have a descriptor on the left. That's our manifest. We have a system of record in the middle where we store it. We have an operator that reacts to that and provisions things, and we output resources or things on the right. And so in the case of databases, you might have a database manifest here on the left, gets stored into Kubernetes. We have an operator which watches that and outputs a whole bunch of random resources on the right. The cool thing here is that the platform's completely in control. We can update the code of that operator whenever we want. Say we want to, I don't know, not use IAM roles anymore, we can delete that IAM role. Say we want to apply a default policy that we were saying everything that looks like this needs a policy, we can apply that. The user doesn't need to do anything. Their intended state still reflects their intended state. And so that really makes up the core of the provisioning capability. We have the storage of manifest somewhere, we react to it and output a resource. Because we're storing within a namespace or within a folder, it also gives a fairly natural way to model environments. So you can see we have a development namespace up the top where we store development resources and we output development things to AWS and Databricks. We have a staging namespace, operator picks up on that, outputs things to staging. If we wanted 20 new environments tomorrow for some reason, we just add more namespaces. Everything just works. It's pretty easy. In addition to that, we have two more components that I need to talk about. So you can imagine if we just gave users access to put things into Kubernetes, we'd end up with spaghetti again because we have no way of validating that our metadata graph makes sense. And so these two components work together to let users register things into the system in a way that conforms to our validation rules. The first part of this is the gateway service. The gateway service is really the only part of this which is traditional Kubernetes usage. It's just a microservice that sits around. It translates requests with descriptors in them into things Kubernetes understands. Perry was talking about things like PRGB or like greenfield validation, and we do that here. We terminate the authentication up the top. Once objects are stored into Kubernetes, we have emission controllers. These are native extensions in Kubernetes that let you validate things before they're stored in the database. So we can see here we're going to apply some rules to this script up here. So for example, a rule might be your databases, if they live in the source layer, must look like this. Fluid itself can also have rules on things like you can't delete a database while another database references it, and referential integrity rules which keep the metadata graph clean and sensible. And all of these are extensible. You could have more rules for more platforms or more rules for more business stakeholders if you wanted to. And so with that, we have really the core of the metadata storage and provisioning system. We have the ability to get data into a database, make sure that it makes sense in the context of everything else in that database, and provision resources based on it. Cool. There's kind of two things to tack on here. These are mostly, for example, most of our users come in via Bitbucket, and so they come in via CI system, just good to know. The other thing is that the data in Kubernetes isn't optimized for complex queries. So if you want to do a query like, what is my full lineage of my data from start to end? Kubernetes internally represents things as a key value store. It's going to suck when you try and do that. So we replicate some of the data out into a few different sinks, one of which is Compass, which is our internal data catalog. Cool. So with that, we have the ability to declare what users want in the lake. We have the ability to store it in a format that makes sense. We have the ability to provision things based on it, and everyone's happy. So I'm going to do a quick demo. It's recorded. Our goal here is mainly to deploy a flow, which is a data pipeline, which writes 2 rows into a table called Pokemon Mons. I'll also be deploying a few other resources, but it doesn't really matter what they do. Cool. So hopefully this works. Wow. Lag. Space to start. Cool. So I'm going to start off by initializing a data product. You can see I'm using dbt here. You can really just have a repo full of YAML files if you really wanted, but we're going to use dbt because it's cool. This is going to set up some code for us. I'm going to cut to the code. I'm going to start off by just creating a SQL file, and this is the SQL that we're planning to run. It's going to insert 2 rows of like Pokemon information into a table. I also need a dbt model file. If you haven't worked with dbt before, don't worry about it. What I'm trying to demonstrate here is that when I talk about Fluid being the language of data, it's a language that we receive and we understand. If you want to write dbt or something else which can compile down to Fluid, we're fine with that as well. In fact, we want dbt to be the tool of choice, and so we're going to show that we can compile dbt down to Fluid by pressing that button up there. So once this compiles down, it takes like a second. You can see we have a table created for us, and that table is a Fluid descriptor. Some of the IDs here are a bit longer than I showed you before, but at its core, it is a table called Pokemon Mons with a description and a few columns in it. Yeah, so once I have that, I'm going to deploy that into our platform staging environment. Most of our users will come in via a CI environment like Bitbucket, but I have admin access and I have a staging environment, so I thought I'd use it. I made a typo here that I forgot to edit out, so unfortunately you'll have to wait for me to type faster. Also, you can enable Vim key bindings in your IDE, which is really cool. Anyway, cool, so that deploys it into our staging environment. You can see it registers the descriptors, and so this bit does the metadata storage and validation. And very quickly, you're going to see a bunch of rows appear, and this is the actual provisioning loop. So give it a sec. We've provisioned a database, 3 databases over here. I'm going to cut to the end of this. Also, I'm sorry that the output is a bit ugly. Hurry up past me. Cool, so you can see we've provisioned 5 resources. There's like a bunch of databases, a table up here, and a data product down here. I'm going to hop into Kubernetes real quick, and I can show you what's happening behind the scenes. So I'm going to list all the tables and grep for the one called Pokemon Mons. It's up here. I can grab the YAML out of Kubernetes as well. You can see that there's like a bit of garbage down here, but like our descriptor is also in here, which is nice. And so we get free admin tooling with Kubernetes, which is cool. You can do the same thing for databases. I'm not going to print out all the YAML because it's boring. But you can see our 3 databases are provisioned and ready as well. Obviously, this isn't that useful, so I'm going to also show you what's happening in Databricks. You can see we have our database provisioned up here as a schema. And if I pop into the database we care about, this one, you can see there's a table in it. It has columns, they have descriptions, and we have sample data, and there's nothing in here. So we provisioned the table in the database just based off YAML files. User never worried about it being a UC schema table or a UC schema database. It just happened. But our goal now is to get some data in it. And so following along that trend, we're going to build a dbt project. You might notice that, where's my latest pointer? You might notice here that the user has declared that they want a dbt project to run. They want to run this test Pokemon dbt project. At no point have they worried about, I want an Airflow job, I want an Airflow DAG, I want a Databricks job. They're just saying, I want my dbt to run on this schedule. And then we figure out what happens behind the scenes. The way we compile dbt internally is we build it into a Docker image. There's probably a talk hidden in like the few lines of text down here, so I'm not going to talk too much about it. But I'm going to skip to the end. We've built it. We're going to grab the tag. We're going to tell it that we want to run this Docker image. Again, no Airflow, nothing specific. And so users just tell us what they want. We're going to deploy that again. This one should be pretty fast because we're just deploying Airflow DAG at the end of the day. And so in a second, you'll see, I made a typo, sorry. So there is a status field that I'm missing. So this is an example of the validation output. You have to declare your lifecycle status of all your resources. This one is available. There are also like decommissioned and deprecated statuses as well. Once I fix that, I can deploy it. And we should get a link to an Airflow DAG sometime in a second. Pause. Cool. Airflow DAG is being opened. I'm going to drag it across. Once it is. Cool. So there is an Airflow DAG up here that's been provisioned. We're going to trigger the DAG. It's going to run a job. And this is fast forwarded. I wish my Airflow DAGs ran this quickly. Cool. And so if we look at the table now, we should have some data in it. Hurry up. Cool, so there's some data in it. Again, user has declared that they want dbt to run. They haven't declared anything else. They're just tables and YAML descriptors from their perspective. That's pretty cool. So hopefully we've shown a system that self-serve uses, where users declare what they want to exist in the lake without worrying about how it's done, and the platform has full control over the lake and is able to manage and vet the process. Thank you very much.